Welcome to this walkthrough of LeetCode problem number 150, Evaluate Reverse Polish Notation. In this problem, we'll explore how to compute the result of an arithmetic expression given in reverse Polish notation, a unique mathematical notation often used in stack-based evaluations. Let's dive in and break it down step by step. In this problem, we are tasked with evaluating an arithmetic expression given in reverse Polish notation, or RPN for short. Reverse Polish notation is a mathematical system where every operator follows all of its operands, making it a postfix notation. For example, the infix expression 2 plus 1 by 3, which is how we commonly write arithmetic, would translate to 213 plus in RPN. The challenge here is to compute the result of such expressions efficiently. The input will be provided as an array of strings called tokens. Each element of this array will either be an operand, which is an integer, or an operator, such as plus, dash, asterisk, or forward slash. The output will be a single integer that represents the result of evaluating the entire RPN expression. To solve this, we will rely on a stack-based method, pushing numbers onto the stack, performing operations as we encounter operators, and finally returning the single result left in the stack. Now, let's break down the process step by step. Operands, which are the numbers in the expression, are pushed onto a stack as they appear in the tokens. When an operator is encountered, the required number of operands is popped from the stack. For binary operators like plus, dash, asterisk, and forward slash, this will usually be the top two elements. After popping, the operation is performed, and the result is pushed back onto the stack. By the end of the computation, there will be exactly one element left in the stack, which is the final result of the expression. Keep in mind that for division, we are using integer division where the result is truncated toward 0. Let's solidify this understanding with an example. Consider the input array 2, 1, plus 3, asterisk. Initially, we push 2 onto the stack, followed by 1. When we encounter the plus operator, we pop 1 and 2, compute 2 plus 1 to get 3, and push this result back onto the stack. After that, we push 3 onto the stack. The next operator in the tokens is asterisk, so we pop the top two elements, 3 and 3, perform the multiplication to get 9, and push the result back onto the stack. At this point, the stack contains only one element, which is the final result, 9. Another example will help illustrate further. Suppose the input is 4, 13, 5, forward slash, plus. First, we push 4, 13, and 5 onto the stack in order. When we encounter the forward slash operator, we pop 5 and 13, compute 13/5 using integer division, which results in 2, and push 2 back onto the stack. Then, we encounter the plus operator, pop 2 and 4, compute 4 plus 2, and push the result, which is 6, back onto the stack. The stack now contains only one element, and that is the final result, 6. Let's look at a more complex example with nested operations. Consider the input 10, 6, 9, 3, forward slash, minus 11, asterisk, plus, asterisk, 17, plus, 5, plus. We begin by pushing the initial operands 10, 6, 9, and 3 onto the stack. The forward slash operator then pops 3 and 9, performs the operation 9/3, which yields 3, and pushes it back onto the stack. Next, minus 11 is pushed onto the stack, followed by the asterisk operator, which pops minus 11 and 3, computes 3 asterisk minus 11 to get minus 33, and pushes this result back onto the stack. Moving forward, the plus operator pops minus 33 and 6, computes 6 plus minus 33, and pushes minus 27 onto the stack. The asterisk operator then pops minus 27 and 10, computes 10 asterisk minus 27, and pushes minus 270 back onto the stack. Finally, we push 17, compute minus 270 plus 17, push the result, minus 253, then push 5, compute minus 253 plus 5, and end with the final result, 22. The final result of this complex calculation is 22 foot. Now, let's review the constraints and edge cases. The number of tokens will range from 1 to 10,000, and each token will either be an operator or an integer between minus 200 and 200. The input is guaranteed to represent a valid RPN expression, so no need to handle invalid cases. The result will always fit within the range of a 32-bit signed integer. Some edge cases to consider include expressions with a single operand, such as 42 foot, which evaluates to 42. Another is division with negative numbers, such as 7, -3, /, where integer division truncates towards 0, giving a result of -2. Finally, for very large inputs with nested operations, the solution needs to handle up to 10,000 tokens efficiently. By understanding these scenarios, we can ensure our implementation is both correct and robust. To solve LeetCode problem number 150, our goal is to evaluate an arithmetic expression given in reverse Polish notation, or RPN. The structure of RPN makes it well suited for a stack-based approach, as the postfix nature allows operators to act directly on the most recent operands. The first approach we considered is a brute force method that simulates RPN evaluation. The intuition here is straightforward: traverse the tokens one at a time, and for each token, determine whether it's a number or an operator. Numbers are pushed onto a stack, while operators pop the top two numbers off the stack, perform the operation, and push the result back. This process continues until all tokens are processed, leaving the final result on the stack. This approach has a time complexity of O(n), since each token is visited once, and a space complexity of O(n), due to the stack. While efficient and easy to implement, edge cases like division by 0 or handling negative numbers require extra care, making it slightly less robust in some scenarios. Another approach is recursive evaluation. This method leverages the structure of RPN by breaking it down into smaller subproblems. The idea is to process operators recursively, identifying their operands and solving from right to left. This approach allows us to evaluate the expression in a divide and conquer manner. However, while the time complexity remains O(n), and the space complexity is also O(n), due to the recursive stack frames, this method introduces additional challenges. It's harder to implement and debug, and for very large inputs, the recursive depth could lead to stack overflow errors. Additionally, we explored a hybrid approach using a DEEC, or double-ended queue, which could simulate a stack while providing flexibility to process tokens bidirectionally. However, this adds unnecessary complexity without offering significant benefits over the simpler stack-based approach. Both the recursive and hybrid methods have their merits but are less practical compared to the stack-based solution. The stack-based approach was ultimately chosen as the best strategy for solving this problem. It's both simple and efficient, aligning perfectly with the mechanics of RPN. In RPN, operands are pushed onto the stack, and operators act on the most recently added operands in a last-in, first-out manner. This aligns directly with how stacks operate, making the implementation intuitive. Key considerations include ensuring that division operations truncate towards 0, as required by the problem, and correctly handling negative numbers. The efficiency of this method lies in its linear processing of tokens, with each token being handled exactly once. The simplicity of the stack-based approach makes it easier to both implement and debug, while its minimal overhead ensures optimal performance. Additionally, the clear mapping between the problem's requirements and the stack operations enhances the readability of the code. In terms of trade-offs, the stack-based approach stands out compared to recursion. While both approaches share the same time and space complexity, the stack avoids potential recursion depth issues and offers a more intuitive solution for this problem. Recursion can be harder to debug and less practical for large inputs, whereas the stack-based method is straightforward and robust. The chosen approach balances clarity, efficiency, and reliability, making it the ideal choice for evaluating RPN expressions. By leveraging the natural alignment between RPN structure and stack mechanics, we achieve a solution that is efficient, easy to implement, and well-suited to handle edge cases. In conclusion, the stack-based approach provides the best combination of simplicity, performance, and practicality for solving this problem. To solve the problem of evaluating reverse Polish notation, or RPN, we first need to understand its structure. In RPN, the operators come after their operands. For instance, the expression 2 1 plus 3 asterisk translates to open parenthesis 2 plus 1 close parenthesis times 3 close parenthesis, which evaluates to 9. Our task is to evaluate these expressions efficiently. The key to solving this lies in choosing the right data structure. A stack is perfect for this task because it operates on a last-in first-out principle, which aligns well with the way RPN expressions are processed. Now, the algorithm itself is fairly straightforward. We start by initializing an empty stack. Then, we iterate through each token in the expression. If the token is a number, we convert it to an integer and push it onto the stack. This prepares us to handle operations when we encounter operators later in the sequence. When the token is an operator, such as plus, dash, asterisk, or forward slash, we pop the top two numbers from the stack. It's important to maintain the correct order of operands since operations like subtraction and division are not commutative. For example, if the stack holds 5 and 3, and the operator is dash, the calculation must be 3 to 5 rather than 5 to 3. Once the operation is performed, the result is pushed back onto the stack for further processing. After all tokens are processed, the stack will contain a single element, which is the result of the RPN expression. We then pop and return this value. Additionally, there are some edge cases to consider. For a single operand like 42 foot, the result is simply 42. For division, we use integer division to ensure the result is truncated towards 0, as required by the problem. Lastly, invalid input is not a concern here, as the problem guarantees valid input. The stack plays a central role in this algorithm. It stores operands and intermediate results, offering efficient O1, push and pop operations. The input list represents the postfix expression, and we process each token sequentially. The key operations involve pushing operands onto the stack, popping them when an operator is encountered, and performing the required arithmetic operation before pushing the result back. This algorithm is directly implementable in Python. For instance, we initialize an empty stack and iterate through the tokens. If a token is an operator, we pop two operands, perform the corresponding operation, and push the result back. Otherwise, if it's a number, we convert it to an integer and push it onto the stack. The Python implementation continues by handling each operator case. For addition, subtraction, multiplication, and division, we compute the result and then push it back onto the stack. Division is handled specifically using integer division to ensure truncation towards 0. After processing all tokens, the final result is obtained by popping the lone value from the stack. To illustrate this, consider the example input 2 1 plus 3 asterisk. First, we push 2 and 1 onto the stack. When we encounter the plus operator, we pop 1 and 2, compute their sum as 3, and push 3 back onto the stack. Next, we push 3 from the input onto the stack. When the asterisk operator appears, we pop the two 3s, multiply them to get 9, and push 9 onto the stack. At the end of this process, the stack contains a single value 9, which is our final result. The final result is obtained by popping the stack, which gives us 9 for the example. Now, let's analyze the algorithm's complexity. The time complexity is O(n), where n is the number of tokens, because each token is processed exactly once. The space complexity is also O(n), as the stack can hold up to n/2 elements in the worst-case scenario, which occurs when all tokens are numbers before any operator appears. To optimize further, we can directly handle tokens as integers to avoid repeated conversions. Integer division efficiently manages truncation, and combining operand pops with computation reduces the number of stack operations. These optimizations ensure that the algorithm remains efficient and easy to implement while adhering to the problem's requirements. The provided solution evaluates a reverse Polish notation (RPN) expression using a stack-based approach. This is efficient and directly aligns with how RPN is processed. Let's walk through the code step by step. 1. Initialization. The stack variable is initialized as an empty list. This stack will be used to store numbers and intermediate results during the computation. 2. Iterating through tokens, we loop through each token in the input list tokens. Each token represents either a number or an operator. 3. Handling numbers. If the token is not one of the operators, plus, dash, asterisk, forward slash, it is treated as a number. The int function converts the token, a string, into an integer, which is then pushed onto the stack. 4. Handling operators. If the token is an operator, the last two numbers are popped from the stack. Since RPN uses a postfix order, the second last number becomes the left operand, A, and the last number becomes the right operand, B. Depending on the operator, the corresponding operation, plus, dash, asterisk, forward slash, is performed. the result of the operation is pushed back onto the stack. For division, we use int a/b to ensure the result is an integer, as required by the problem statement. 5. Final result. Once all tokens are processed, the final result of the RPN expression will be the only item remaining in the stack. This value is returned as the output. ###edge cases. Single number input like 3 is handled correctly since no operations are performed, and the stack simply contains the number. Division results are truncated towards 0, as required, e.g., int -7/2 results in -3. Invalid inputs, e.g., empty lists or malformed expressions, are not explicitly handled but would raise errors naturally if encountered. This implementation is efficient, with a time complexity of O(n), where n is the length of the input tokens. This is because each token is processed exactly once. The space complexity is also O(n), due to the use of the stack. Here, we begin by importing the necessary Java utilities, specifically the stack class, which will be integral to our solution. The method eval_rpn takes an array of strings called tokens, which represents the input reverse Polish notation expression. We initialize a stack of integers to help evaluate the expression. Then, we iterate over each token in the input array. If the token is not one of the 4 operators, plus, minus, multiplication, or division, it must be a number. In that case, we parse the token into an integer and push it onto the stack. However, if the token is an operator, we pop 2 elements from the stack. The first popped element is treated as the second operand, and the second popped element is treated as the first operand. Using a switch statement, we then perform the relevant operation based on the operator token. For example, if the token is a plus sign, we add the 2 operands and push the result back onto the stack. Similarly, for subtraction, multiplication, and division, we apply the respective operations and push the results back onto the stack. After processing all the tokens, the loop concludes, and the stack contains one final value, which represents the result of the reverse Polish notation expression. We simply return this value by popping it from the stack. This approach ensures that we handle the expression in the correct order of operations, as the stack structure naturally respects the postfix notation's requirements. The method is efficient and concise, leveraging the stack to evaluate the expression in linear time proportional to the length of the input array. In this example, we are solving a basic arithmetic problem using reverse Polish notation with the input tokens 2, 1, plus 3, asterisk. We start with an empty stack. First, the token 2 is processed. Since it's a number, we convert it to an integer and push it onto the stack, resulting in a stack of 2. Next, the token 1 is processed. Similarly, it's a number, so we convert it to an integer and push it onto the stack. Now, the stack contains 2, 1. Then, the token plus is encountered. As this is an operator, we pop the last 2 numbers from the stack, which are 1 and 2. We perform the operation 2 plus 1, which equals 3, and push the result back onto the stack. At this point, the stack contains 3. Now, we process the token 3. Since it's a number, we convert it to an integer and push it onto the stack, resulting in a stack of 3, 3. Next, the token asterisk is encountered. This is an operator, so we pop the last 2 numbers from the stack, which are 3 and 3. We compute the result of 3 asterisk 3, which is 9, and push it back onto the stack. At the end of the process, the stack contains 9. The final output is the last remaining number in the stack, which is 9. In this example, we are evaluating a more complex expression involving division with negative numbers using the tokens 4, 13, 5, /+. Starting with an empty stack, we first process the token 4. Since it's a number, we convert it to an integer and push it onto the stack, resulting in 4. Next, we process the token 13. Similarly, it's a number, so we convert it to an integer and push it onto the stack, resulting in 4, 13. Then, the token 5 is processed. As another number, we convert it to an integer and push it onto the stack, giving us 4, 13, 5. Now, the token / is encountered. Being an operator, we pop the last 2 numbers from the stack, which are 5 and 13. We perform integer division, computing 13 //5, which equals 2. This result is pushed back onto the stack, leaving 4, 2. Next, the token plus is processed. Again, as an operator, we pop the last two numbers from the stack, which are 2 and 4. We compute the operation 4 plus 2, which equals 6, and push the result back onto the stack. At the end of the process, the stack contains 6. The final output is the last remaining number in the stack, which is 6. Here, we are solving a more complex expression with the input tokens 10, 6, 9, 3, /11, plus, 17, plus, 5, plus. Initially, the stack is empty. We start by processing the first 4 tokens, 10, 6, 9, and 3. Since these are all numbers, we convert each of them to integers and push them onto the stack sequentially. At this point, the stack contains 10, 6, 9, 3. Next, the token / is processed. This is an operator, so we pop the last two numbers from the stack, which are 3 and 9. We compute the result of 9 / 3, which equals 3, and push it back onto the stack. The stack is now 10, 6, 3. Then, the token -11 is processed. Being a number, we convert it to an integer and push it onto the stack, resulting in 10, 6, 3, -11. Next, we encounter the token asterisk. As an operator, we pop the last two numbers from the stack, which are -11 and 3. We compute the multiplication 3 *-11, which equals -33, and push the result back onto the stack. The stack becomes 10, 6, -33. Then, the token plus is processed. This is an operator, so we pop the last two numbers from the stack, which are -33 and 6. We compute the addition 6 plus -33, which equals -27, and push the result back onto the stack. The stack now contains 10 minus 27. After that, the token asterisk is processed. Again, as an operator, we pop the last two numbers from the stack, which are -27 and 10. We compute the multiplication 10 *-27, which equals -270, and push the result back onto the stack. At this point, the stack contains -270. Now, the token 17 is processed. Since it's a number, we convert it to an integer and push it onto the stack, resulting in -270, 17. Then, the token plus is encountered. This is an operator, so we pop the last two numbers from the stack, which are 17 and -270. We compute the addition -270 plus 17, which equals -253, and push the result back onto the stack. The stack now contains -253. After that, the token 5 is processed. Being a number, we convert it to an integer and push it onto the stack, resulting in -253, 5. Finally, the token plus is processed. As an operator, we pop the last two numbers from the stack, which are 5 and -253. We compute the addition -253 plus 5, which equals -248, and push the result back onto the stack. The stack now contains -248. At the end of this complex expression evaluation, the last remaining number in the stack is -248. This is our final output. By following the principles of reverse Polish notation, we've broken down the computation step by step, handling numbers and operators sequentially to arrive at the correct result. To analyze the time complexity of the eval_rpn function, let's break it down step by step. First, the function iterates through the tokens list exactly once. If we denote the number of tokens as n, this iteration contributes O(n) to the overall complexity. Next, for each token, we either append it to the stack if it's a number, or, if it's an operator, we pop two numbers from the stack, perform the arithmetic operation, and push the result back onto the stack. All of these operations, whether pushing, popping, or arithmetic, are constant time operations, or O(1). Since every token is processed exactly once, and each processing step takes O(1) time, the total time complexity for the function becomes O(n). Now, let's examine the space complexity of the eval_rpn function, which is primarily determined by the stack used to store intermediate results. In the worst-case scenario, all operands are pushed onto the stack before any operators are encountered. For example, in an input like 1, 2, 3, plus, asterisk, the stack temporarily holds all three numbers before reducing. If the input contains n tokens, the maximum stack size in such cases will be proportional to n, leading to a space complexity of O, n. Apart from the stack, the function uses a few local variables, such as a, b, and token, which require constant space, or O1. Since these do not grow with the input size, they do not affect the asymptotic space complexity. Therefore, the overall space complexity is dominated by the stack, resulting in O, n. When comparing this approach to other potential methods, we find that reverse Polish notation is inherently efficient. It avoids the need for handling parentheses or operator precedence rules, which are common challenges in evaluating infix expressions. Because of this, there's no meaningful brute force alternative to contrast against. The stack-based approach we're using here is both optimal and well-suited for this problem. With linear time and space complexities, O, n, for both, it achieves the best possible efficiency for evaluating RPN expressions. Whether in the best, average, or worst case, the function processes all tokens exactly once, maintaining O, n, time complexity. Similarly, the stack may grow to its maximum size in the worst case, but that also results in O, n, space usage, making the approach consistently efficient across scenarios. To mathematically prove the time and space complexities, consider that each token contributes a constant amount of work. Whether it's a push, pop, or arithmetic operation, each step is O1. With n tokens in the input, the total work is O, n, multiplied by O1, which simplifies to O, n. For space complexity, the stack grows linearly with the number of operands, as each operand is pushed onto the stack before being reduced by operators. This results in O, n, space usage in the worst case. By combining these observations, we can confidently state that both time and space complexities are O, n, and this conclusion is supported by mathematical reasoning. When working with reverse Polish notation, there are several common mistakes to watch out for. One frequent issue is not handling division properly. Integer division in RPN should truncate towards 0. For instance, dividing -7 by 2 should result in -3, not -4. Using the standard division operator without accounting for this can lead to wrong results. Another mistake arises with operand order for non-commutative operators like subtraction and division. Keep in mind that these operations depend on the order in which operands are processed. For example, for 2- in RPN evaluates as 4 minus 2, not 2 minus 4. Always ensure the second value popped from the stack becomes the left operand. Additionally, failing to validate the input thoroughly can cause problems. Invalid tokens or insufficient operands for an operator might be present, and if you don't check for these, runtime errors can occur. Make sure the stack has enough operands before applying an operator. Stack underflow is another common issue. This happens when you try to pop from an empty stack, which can crash your program. Finally, edge cases are often overlooked. These include scenarios like having a single operand, such as 42, or invalid expressions like +*1. Ensure your solution handles such cases gracefully to avoid unexpected failures. Now, let's discuss some important insights for tackling this problem in an interview setting. First, the primary goal here is to simulate stack operations effectively while addressing edge cases. Demonstrating robust error handling and clearly explaining your use of the stack to process the expression are key to making a strong impression. It's also valuable to recognize patterns across similar problems. Many challenges involving postfix or prefix notation leverage stack-based techniques, so mastering these mechanics will be beneficial for a wide range of problems. Interestingly, optimization isn't a major concern in this case. Given that the input size is typically small, your focus should be on correctness and clarity rather than performance. When explaining your approach, consider discussing trade-offs. For example, while stacks are the ideal data structure for this problem, you might briefly mention why alternatives like queues are less suitable. Additionally, building connections to related problems can demonstrate your broader understanding. Examples include LeetCode 20, which involves validating parentheses using stacks, and LeetCode 394, where stacks are used to decode nested string patterns. Other problems like LeetCode 224 and 856 also rely on stack-based logic to evaluate expressions, making them great practice for honing these skills. Finally, let's explore some alternative methods to solving this problem. One option is a recursive solution, where you convert the RPN expression into a binary expression tree and evaluate it recursively. While this approach is elegant and can deepen your understanding of expression trees, it comes with higher memory overhead and is generally less efficient than using a stack. Another alternative is a two-pass solution, where you first convert the RPN expression into infix notation and then evaluate it. While this method reinforces concepts of expression parsing, it's more complex and prone to errors, so it's not recommended unless explicitly required. The key takeaway here is to focus on mastering stack operations and handling edge cases effectively. In interviews, prioritize clarity and robustness in your solution. Avoid overcomplicating the problem with alternative approaches unless the interviewer specifically asks for them. By keeping your solution straightforward and emphasizing core principles, you'll be well prepared to tackle this challenge and similar ones with confidence. Thanks for staying until the end of this video. To summarize, we solved the problem using a stack-based approach with linear time and space complexity. Reverse Polish notation is an essential concept for stack-based evaluations, and mastering it will help you tackle similar problems. Be sure to subscribe for more solutions and tips. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!